All right, y'all, day 4. This is the last one. This is such a long unit for 1D, so this is the last one. So we're going to talk about something completely different. So we went through all of this with stocks, right? So we know that our shape, we know how to label the shape now. We know how to find our outliers. We know when to use mean versus median, and we know how to calculate our standard deviation or our IQR. So we know all of these different terms. So what's going to happen at this point is we're going to get a distribution, and with this distribution, it can be dots, it can be histograms, but we're going to have something in here that's going to look like some distribution of data. And with this distribution of data, we're now going to plot this curve, and it could be something that looks like this. It could be something that's going to look very standardized, and we're going to be able to pull data from these curves. And that is where this concept of measuring precision with a percentile comes in. And so what we want to do is one way to describe an individual position within the distribution of quantitative data is to calculate the individual's percentage. And so what we would say is something is the xth percentage or the pth percentile of a distribution. Now, very important. So our percentile, as we're going to calculate this, is always going to be less than or equal to. So if we had a value that was in here and we wanted to know what this value was, this is all of the data that we would look at that would be less than or equal to whatever this p percentile is that I'm trying to calculate. Okay? Now, this is verbiage, but it's really important. So a percentile is a specific point. Now, when we're calculating the percentage of observations, it's everything that's less than or equal to always. But if we want to know a specific percentile, it is a point. So because of that, an observation isn't in the 84th percentile, it is the 84th percentile, or it's at the 84th percentile. So you have to use this term either at or is. We wouldn't say that some value is in. The difference is, if I wanted to know this point right here, this point has a specific p percentile. It is at this percentile. Yes, it might be within this range, but the specific point is at that percentile, okay? So they are usually reported as whole numbers. So if 50 out of 75 data values are less than or equal to a specific observation, how should we report this percentile? So 50 out of 75 is going to be 0.667, okay? So what we would say is that it is at the 67th percentile. Now, because stats is a little quirky, you could also get credit for this if you said it's at the 66th percentile. And I know you'd be like, well, this rounds to 67, but in stats, because it's quirky, 66th percentile would also work. Okay, so what does this mean? This means that the median is roughly at the 50th percentile, and the first quartile is at the 25th percentile, and the third quartile would be at the 75th percentile. This should sound very familiar. We just saw this when we did a box plot, okay? So let's do an example. So it says, people are living longer now than any time in recorded history. This is a blessing, but also a challenge for countries because they must adjust to the needs of their aging populations. One statistic important to the social scientists who study this phenomena of life expectancy at birth. The STEM plot shows the life expectancy at birth in a recent year for 41 countries in Central America, South America, and the Caribbean. Okay, so here's the key. So 8/2, which means that this guy hold on, let me fix my camera. That means that this guy here is 82 years old, 8/2. All right, so it says calculate the percentile for a country with a life expectancy of birth at 78 years and interpret the value. Okay, so 78 years is going to be right here. And if you remember, it's going to be at or less than or equal to. So I have 41 countries. That's what all of this data is. It tells us up here. So if I count all these data points, I have 41 data points on here. And I want to know how many of those are going to be what is the life expectancy? So 78, so I'm going to cut it off right here. That's where 78 is. So I have 1, 2, 3, 4, 5. There are only 5 countries that are going to be greater than that. So if I have 41 minus 5, this is going to be 36. So if I take 36 and divide this by 41, I don't know this one, I get 0.878. So I would say that the country, this is my interpret, the country is at the 87th percentile in the distribution with a life expectancy of 78. Okay? All right. The life expectancy at birth for Peru is at the 39th percentile. Let me change my color here so I can see this better. So we're at the 39th percentile. How many years is a Peruvian newborn expected to live? So we're at the 39th percentile. So really, if you think about what this is asking, is we're at the 39th percentile and we have 41 countries, right? So what is 39% of 41? So 0.39 times 41 is 15.99. Okay, so what this is saying is that the 16th value, this is what I'm looking for. So the 39th percentile of the 41 countries is 16. So if I count to my 16th here, I would have 1, 2, 3, 4. Right here. So that's this value at 72. So my interpret sentence here would be Peruvians are expected to live to be 72 years old. Okay, so this is how we use this concept of a percentile when we have data, right? Okay, let's keep going. Okay, so this is one of the most important concepts of the entire year. And this is going to carry forward into every single unit that we have moving forward. So another way to describe an individual's position within a distribution is something called a standardized score. And we use this concept of a z-score. So it's a standardized score. And we call it a z-score. Okay. The standardized score, the z-score, for an individual value in a distribution of quantitative data tells me how many standard deviations from the mean the value falls and in which direction. So if we have a positive z-score, then it's going to be to the right. If we have a negative z-score, it's going to be to the left. Now, we have a formula used to compute z-score. So my z-score is going to be my value minus my mean divided by my standard deviation. A lot of times you're going to see it like this. We have some value minus our mean over our standard deviation. Okay, and this, you just have to memorize this. You have to know it. Your calculator is going to give you z-score, but sometimes you have to work backwards. You have the z-score and you want to find the mean, or you want to find the standard deviation. So you have to know how it all plugs in, because that your calculator won't do. Okay, so values larger than the mean have a positive z-score. Values smaller have a negative z-score. And notice that standard deviation has no units. Okay, so our z-score, because we have no units here, our z-score is not going to have any units on that, right? It's just going to be a value. Okay, so let's practice this. So the previous example, we talked about life expectancy for 41 countries. Summary statistics are shown below. Okay, so here's my summary statistics. This part of it right here is my 5-number summary, little review. So this is my 5-number summary, the 5 numbers I need, but I also have the mean and the standard deviation. Calculate and interpret the z-score for Peru, which has a life expectancy of 72 years. So what I know is that my z-score is going to be my value minus my mean divided by my standard deviation. Well, my value in this case is 72. So my z-score is going to be 72 minus my mean, which is 73.415, all divided by the standard deviation of 4.159. So when I plug this in, I get a z-score of negative 0.340. Okay, so what does this mean? This is the interpret part, which is super important. So what this means is the life expectancy for Peru is 0.34 standard deviations less than, that's where this negative comes in, so less than the mean of all 41 countries. So life expectancy in Peru is less than the mean. How much less? 0.34 standard deviations less. Okay. Now, here it says the life expectancy for Panama has a standardized score. So standardized score, this is my z-score, of 0.62. How many years is a Panamanian newborn expected to live? This is why I said the formula is so important. So my z-score here is 0.62. I want to know how long they're going to live, so that's going to be their age that I have right here. I know my mean is 73.415, and my standard deviation is 4.159. Now, here's where a little bit of algebra comes in, all right? So I'm going to get rid of this denominator first, so 0.62 times 4.159, and now I'm going to add that value of 73.415, and that gives me an age of 75.99. So my age here is going to be 75.99. So my justify, how would I write this? Panamanian can expect to live to approximately 76 years old. Okay, so what is this concept of a z-score really about? Why do we do this? So we do this to compare values to a single standard. In this case, we can calculate individual data from this standard or from this z-score, but a lot of times you're going to have two things that are not related and you want to compare them. So we have to standardize them so that we can compare values to a single standard. We're going to have an example of that here in just a second. Okay. All right. So transforming data. So we're going to talk about two different ways in which we may need to transform data. So the first thing is, and this all kind of goes back to standardizing. Like why would we need to do this? So if we need to change units in a data set. So one example, let's say you have one data set that's in Fahrenheit and one data set that's in Celsius. And so we would need to change the units, so transform some data to make sure that we're comparing the same same units, right? Another reason that we might do this is if a measuring device, DEVI, device is miscalibrated. So for example, you go through, you measure everything, and then you find out that you weren't supposed to include, I don't know, something happened with your calibration. Let's say you're in chemistry class and you're measuring some chemical, and then you forgot to subtract out your paper. And so you've got to change this whole thing, okay? Bad example, but let me give you this. So the effect of adding or subtracting a constant. So let's just say, for example, that we took a test and I decided, you know what, I'm going to curve it by 5 points. I'm going to add 5 points to everybody's test score. So here's the original test. And if I add 5 points, literally all that I did here is I shifted the whole thing by 5 points. So we see the original number of 25 tests or 25 samples. There's 25 dots in here if you were to count them. The mean of the first one was 35.7, the standard deviation. And so when I add 5 points, the only thing happens is it shifts. My standard deviation doesn't change because the difference or the distance from the mean didn't change. It just shifted. Same thing here. The only thing that happened is that my values all went up by 5. So if we're adding the same positive number or subtracting the same number from each value, then the measures of center, which is the mean or the median, all we're doing is we're adding. This does not change the measure of variability. So the standard deviation or the IQR. Or the range, I guess. I think that's what I meant to have there. So it doesn't change the standard deviation, the IQR, or the range. Nothing changes if we're just adding or subtracting to the same value. It does not change the shape of the distribution. All it does is shift data. In this case, we added 5 points, so it shifted it to the right. But if I subtracted 5 points, it would shift it to the left. That's all that happens. So now let's say that the test was really a bust, and I'm going to double all your test scores. So you got a 40. If you got a 40 on it, then I'm going to double it, and it's now an 80. So if we look at what happened here, so here's my initial number. Here's my doubled number. So as that happens, look what happens to my data. My data spreads out significantly. So here, this is pretty tight. After I multiply this out and it doubles, my data looks significantly different. So because it's spread out, that means my standard deviation is going to change. And we see that over here. The standard deviation changes. Okay, so the mean is just doubled, but the standard deviation changes, which means my IQR is going to change. So if we're multiplying or dividing by the same positive number, so we're multiplying or dividing by some value, it multiplies or divides the measure of the center. So the center is affected, we multiply. It also changes the variability. All right, so now this changed by 2. I multiplied this. Now, it doesn't change the shape of the distribution. All it does is spread it out. If you look, we still have a peak here. If you see this little shape right here, we have that modeled down here between 90 and 100. So the shape of the distribution didn't change. It just spread it out. Remember, up here, it does not change the variability when we're adding, but when we're multiplying, it does change the variability. So that's why it's spread back out. Okay? All right, so we got a big space there, but flip it over because we have an example problem. Okay, so what happens if we change both adding or subtracting a constant and then multiplying or dividing by a constant? And so with this, we're just going to use our order of operations. Okay, so you're going to multiply and then add. Okay. All right, so here's a problem. Let's go through this. It says, this pasta emporium is an authentic Italian restaurant that makes its own pasta. The rigatoni is so popular, customers buy 32-ounce boxes of rigatoni to cook at home. Employees who fill the boxes aren't perfect, however, so the actual amount in the box varies. To check their work, she selects 50 boxes at random from 1 week's production. And here's a histogram of that. So we have this histogram, and we also have our 5-number summary and our mean and standard deviation. Okay, so worried that the boxes are being underfilled, she adds an extra 0.5 ounce of rigatoni to each of the 50 boxes so her customers wouldn't feel cheated. So calculate the mean amount of rigatoni in these 50 boxes with the extra pasta in each box. So here's what I have. I have a mean right now of 31.70. So that was the mean distribution. And I'm going to add 0.5 ounces. So if I add this, I now have 32.20 ounces. So will the customers be satisfied? So it tells us up here that it's a 32-ounce box. So if she's adding this extra 0.5 of an ounce in here, yes. The customer should be satisfied because 32.20 is greater than 32 ounces. Just barely, but it's bigger. They're not getting cheated. Because some customers had recipes that used the metric system, so grams to ounces, the refilled boxes were relabeled to show the amount of rigatoni in grams. So what shape, mean, and standard deviation would the distribution of the amount of rigatoni in grams have? So now what we have is we've got this mean here, and our mean value is 28.35. So we have 28.35 grams, and we're going to multiply this because remember, we're going from ounces to grams of our 30, I'm going to write this the long way, 31.7 plus 0.5. Now, I could take this value of 32 and just plug it down in here, but this I wrote this out this way just so you see where this comes from. So when I plug this in my calculator now, I have 32.2 times 28.35. So this gives me 912.87 grams. Okay, now with this, so with a mean, we're going to add and we're going to multiply. All right, now let's talk about the standard deviation. So my standard deviation is 28.35, so that's my conversion. And my standard deviation up here is 0.35. So let's go back to, sorry, it's on the other side. Let's go back to this. So when we're adding, right, when we're adding, it doesn't change the variability. Adding only changed the center. So when I'm changing my variability, I don't add the 0.5. So I have 28.35 times 0.35. This is my standard deviation. And this is going to give me, 9.923. Okay, so standard deviation, no adding. All I did was multiply. All right, and then what happens to my shape? That was the last thing it asked us here. I guess technically that was the first thing. Shape, mean, and standard deviation. So there's no change. And I'm going to look at this distribution up here. And I'm going to say that this distribution is roughly symmetric. With one possible low outlier. Now, I could go in here and I could calculate this, but I'm not going to. It's just asking what happens to the shape. It's not asking if I have any outliers. So I would just list that as my one possible outlier. Okay? All right. So now we're going to put all together a transformation with a z-score. So here's what I have. I have this. What happens if we standardize? So standardize, when you see this, think z-score, all of the values in the distribution of quantitative data. So if I take all of this data and put it all together, what is going to happen? So with the shape of the distribution of z-scores is always the same. It doesn't change. So it's the same as the original distribution. Any outliers, so the placement of the outliers are also the same. Our outliers aren't going to change. So in this case, if this was a potential outlier, it would still be an outlier with a z-score. So my center, the mean of a distribution of z-scores is always 0. Always, always, always 0. And the spread or the variability of the standard deviation of a z-score is always 1. And this is so important, I'm going to highlight this. My center is 0, and my spread, my variability, is 1. Always, always, always with a z-score. Okay? So we would get the same results no matter what the original distribution looks like. The distribution of z-scores always has the same shape as the original, always has a mean of 0, and a standard deviation of 1. Now, I'm going to start writing it this way. So with z-score, and people ask me all the time why I put a line in my z, because I don't want to get it confused with a 2. So always what I have here is that my mean, and this is going to be my mean of my population, is going to be 0, and my standard deviation, so this is my standard deviation of the population, is always going to be 1. Okay? All right, so what we have on this back page is just a little bit of AP practice that has you, and this is what some multiple choice questions would look like, which is a little bit of everything that we've done to date. So go ahead and try this, and then we'll go over the results.